So last time, what did we do? I mean, last time we were on DonkeyCar, so installing the simulator, setting up everything, and changing minor config so it works better. So again, if you want to download the simulator, you can go to Ton Kramer DonkeyCar, and in the release, you have one release for Linux, Mac, or Windows. And for those who were not there last time, you can go to my GitHub, and there are two repos we are going to use today. One repo is a DonkeyCar, which has the edits from the live, and so that the first one with some edits, like we removed the limits for steering, we also changed the termination condition, so that's mostly it. So this branch is available here. That's what I'm going to check out also. And the other things we are going to use is also the RL zoo, which is so you can go to RL zoo, and again it's a branch name offline reinforcement learning. And the main difference compared to others is that it has DonkeyCar, which is included in it. It has other stuff, but the main thing is in utils and import env. Here you have the DonkeyCar, which is included, and in the hyperparameters there's also the DonkeyCar, which is included. So let's start almost from scratch. So we are going to clone that repo again. Okay, we're just going to do live number 2, and in live number 2 I'm just going to clone the repo and check out the branch that we modified last time. So it's called fit live twitch, and once we're here we can install it using pip install -e dot, and that will install the package. So that's one thing, and the other thing you need to do if you want to be up to date with the last live is so going to DonkeyCar and download the latest simulator. Once you have downloaded it, you follow just the install instruction, and you should be able to launch it. And if you launch it, then you will have this window, and this will allow you to actually interact. This code will actually interact with this simulator. No questions so far. Maybe I should put the link in the chat so it's easier. Okay, DonkeyCar, here we go. So first link is here. The simulator, you can find it here, and the zoo. So I put all the link in the chat. Here we go. So last time what we did was downloading simulation, connecting to the simulation, and doing some tweaks. But that was actually not enough. If you want to train a good racing agent, you need to actually reduce the observation space, because learning from image directly is really costly and will take a lot of time. So instead, the plan of today is to see how to make everything, how to make the reinforcement learning training much faster by reducing the input dimension. And for that, we're going to use Autoencoder. In fact, denoising autoencoder, also called augmented autoencoder. And the idea of autoencoder is you just have the image as input. You encode it in a small latent space, it's called, to have a latent vector, latent representation of that image. And then using that bottleneck, that small latent vector, you try to reconstruct the input image. To make it more robust to illumination change, or in our case, when we drive with one or more cars, we're going to do some augmentation. And instead of reconstructed the augmented image, the input image, we are going to reconstruct the untouched image. And for that, we are going to use this repo. So it's called, you can also go in my GitHub, and I will put the link again in the chat. And today the idea is to see how do we collect data for this autoencoder, how do we train the autoencoder, how do we test it, and then how do we plug everything so we can actually train a reinforcement learning agent with it. And it has great advantage because the training is much faster. So far so good, no question, no remark, everything's clear. Is the autoencoder approach purely for speed of training, assuming the same number of training cycle in reinforcement learning would expect it to outperform raw images? So actually, the autoencoder is not only for speed of training. Well, it's also because it makes it more robust to change in observation, and also you can actually check out what was learned by the feature extractor, by this encoder. Where with RL it's a bit a black box, and you are not sure what is learned, what is not, and where it may break. Where here with the autoencoder you can directly check the reconstructed image, so you can know what part of the image was encoded or not, and you can check the reconstruction error to see if some images are correctly encoded or not. Where with reinforcement learning, if you do it end-to-end, well, you never know what's encoded or not. Yes, with much more training time, I would expect it to be more or less the same performance or even better, but to be very fragile to change in observation. I hope that answers the question. Perfect. Once we have done that, we're going to also clone that repo. I recently made it up to date. So in the folder next to it, we can clone it. And I will open it in my editor. Let's just remove that. So it's document, RL, racing car. Okay, live number 2, and here we have. So there's one main folder, which is a package which contains the definition of the autoencoder, the data loader, which also has all the augmentation included, and some other script to actually use the autoencoder later. So that's what's inside the autoencoder script. And in addition, we have some config file which tell you what is the input, the raw input sized dimension. And then, in fact, because most of the image is, well, part of the image is not relevant, we're going to crop it. And that's what the region of interest is doing. We're going to crop a bit the top, and so resize it, and then input dim will actually be the dimension of the image that we feed to the autoencoder. Another solution would have been to change the position of the camera to have not to have to crop, because but that would be for another time. So the main thing with a config file is defining the region of interest, so cropping a part of the image that is not relevant, and defining other constants. Those constants here are mostly for controlling with a keyboard. Okay, so once we have downloaded it, we need to also go into it and install the dependencies using pip install -r -e dot, because it's also a package. Okay. And the next things we're going to do is to actually use it and for recording some data. And for that, I already have a script prepared for you. It's mostly using Pygame. So Pygame is just to record the keyboard input. And it has just some smoothing in it. But basically, the idea is we create our environment, and we will step through it for a total number of steps that we defined before. And here, the agent, it's us, so we are going to control the car. And while we control the car, so here we send the action to the environment, which is the steering and the throttle. While controlling the car, we retrieve the observation. And here we are going actually to write each image received by the camera to a folder. And once we have drive around, then we will be able to actually train the autoencoder. So, and here the nice thing about the autoencoder is you don't need to be a good driver. You just need to drive randomly in the environment, so you get really diverse data. And that's what we are going to do. Is there, before I do it, is there any question? And the syntax, so you can always ask for help. So you first need to actually launch the simulator. That's what I have on the right. And the syntax, so for recording data, is you have an argument folder, which is where we're going to record our images. We're going to call that dataset mountain because we are going to write on the mountain track. And then we have also a maximum number of steps, but we can exit early, so I will put to 10,000. In practice, we won't need that much. And we can actually quit the script easily by pressing Q or escape. So once you have the simulator ready and the script ready, you just launch it. It will launch a small window, and as soon as control ready is appeared, then you can control the car. Here I'm just driving as randomly as possible to actually collect really a diverse data set. And I won't need to drive much. I will drive, I don't know, 1, 2 to turn around. And in the meantime, if you have any question, then please write them. And here I didn't disable resetting, but I should have, because then as soon as I touch a wall, it will reset and put me in the start position, which is something I would like probably to avoid. So here, the main idea for data collection of the autoencoder is really to have a diverse dataset that is representative of what you're going to get when training the agent. Okay, here we go. And let's do a last drive on track, last loop. And so once we have collected the data, the next step will be to actually start training the autoencoder, and we will see the representation evolving through the training. Okay, let's say it's good enough. Then we can press Q to exit everything. And now we can actually take a look at what was learned. So we don't need the simulator anymore for now. So we can close it. And if you go to where you stored the images, which is in my case log dataset mountain, here you have a folder with plenty of images. In fact, there's almost 1,000 of images, and you can take a look at what was recorded. And this corresponds, so the goal is really to have a diverse dataset. And you can actually do that several times, and at the end to the training script of the autoencoder, you will be able to pass multiple dataset folder. And in fact, that's what I usually do. I train a first version of it, and then I collect more data, and then I continue training with the additional data. Is there any question? So the next time we're going to do now is take a look at what the autoencoder model look like, what the augmentation look like, and actually start training, because it will take some time anyway. So if you go back to our project, to Autoencoder, in Autoencoder you will have different things defined here. So the autoencoder is just a simple, it's just 4 layer of convolution, followed by a linear layer, which will actually reduce the dimension of the last convolution to something that we want. And the latent, so that Z size is size of the latent space. It's the encoding that you will use, in fact, afterward with the RL agent. And this, usually I keep it small, so below 100, mostly because it works, and you don't, if you make it bigger, then the RL agent will also take probably more time to train, because then there's more information to decode. So that's it, and the decoder is basically the symmetric of the encoder. That's it, and the way we train it, it's in train autoencoder. What we do, well, we load all the images, and we load both the augmented image, which is the observation, and target ops, which is the unaugmented image, the clean image. And what we do is we do a full forward pass through the autoencoder. So we encode the observation, the augmented observation, we decode it, and then we just do L2 loss, so a mean squared error from pixel to pixel between the target observation and the predicted observation, the reconstructed observation. And we're going to iterate as long as possible. And at every epoch, we'll actually randomly sample one image and take a look at what is learned. And at every time that the best model is found, it will be saved. So we don't need to actually wait for the full training to stop to use it or to test it. We can try it before. And I will first start the training, and then I will explain a bit more in detail how do I augment the space, or how do I make it work better in practice. Okay, so to actually train, so we go in our folder. Can I make it bigger? I don't know. And we are going to call, in fact, it's in the README. In the README, if you want, there's the instruction for recording data and instruction for training the autoencoder. And we're just going to copy paste the instruction and adapt it to our case. So here we're going to train the autoencoder for 100 epoch with a small mini batch size. The latent space will be of 32 dimension. And the dataset we're going to use is dataset mountain, and we want actually to see what's happening. I will set it to even more epoch, and here we go. So best is also when you can use a CPU to train, but best is to actually have a GPU. And here you can actually see, so what I said, so the original is the raw camera image. Cropped is one, we have cropped the region of interest. And reconstruction is reconstructed image by our autoencoder. And currently you see it's not good at all, it's just reconstructing very blurry images. So the idea of the encoder is the general idea with the autoencoder to reconstruct lines and omit some of the background that changes more often. Yes, well, the objective that we set for the autoencoder is it will first reconstruct the most salient thing on the salient features on the image, and we hope that it will actually encode the lines. And yes, because the shadows and because of our augmentation, we hope that it will forget to encode information that is irrelevant for us, which is in our case trees, shadows, or things, or other things like that. And here already after 37 epoch, we can see that it has already improved, and we can start to see something, but it's still very blurry, and that's normal because it first reconstructs the main salient thing, and it will only reconstruct the fine detail later on. So we're going to leave that and go back to actually see a bit more in detail what did we do. So one important thing that I did here is to make it robust and to make it reconstruct what I want. I added some augmentation. So augmentation is noise or deterioration that you add to your image, and they should be well thought, because if you do the wrong transformation, it will try to be invariant to that transformation, and sometimes you want actually to encode. For instance, if you reverse the image but you don't reverse the target, it will be invariant to the line direction, and that's something that you don't want. So I mainly added several things. One thing is flipping left and right the image, but then also flipping the target. This is an easy way to augment the size of the dataset. I also added some random shadows, so you can actually check out the code from Osama, which is online. Basically, the idea is to generate random shadows and add that to our image, because if there's shadows on the road, we don't want to encode that, we want to be invariant to that. So I mainly adapted this. Then we had some Gaussian blur to actually remove some details. We had some motion blur in case our camera is moving. We want to be invariant to that. We want to be robust to motion blur. And then there's some additional robustness added. So here it's doing some color jittering. So it's changing a bit the color. So in case the illumination is slightly different, we won't have a problem. And finally, cutout is just masking part of the image. And I will demonstrate that right now. So one way to actually see what's happening on what's reconstructed and what this augmentation code does is, again, you can go to the README and take a look at inspect the trained autoencoder. Again, we're going to copy paste that. And here you can already see, we can see a bit the lines. It's not perfect at all, but it's already something. So we are going to our folder And so here we want to take a look at the dataset mountain, and the autoencoder is already saved here. We're going to take a look at 50 samples, and we want also to take them with augmentation on. That's what the augment is doing. So if we run that script, okay, here we go. So that's the interesting part. So again, we have the original image, to which we apply some augmentation. Here, that's what I was talking about. Those blocks are actually it's the cutout augmentation, which actually masks part of the input and forces the autoencoder to learn from the context to reconstruct what's inside. And because also of this cutout, when I'm driving with cars that were not seen during training, this will also not reconstruct them and not encode their position, or not mess up with the representation. And using the arrow keys, you can actually, using any key, you can actually go through different images. So for instance, here it's when we augmented the image with a random shadow, and here it's the reconstructed image. And that way we can see how robust is our autoencoder. And currently it's not so great, but it's much better than at least at the very beginning. Okay, is there any question? I think I will also continue training the autoencoder more to actually have a better reconstruction. And the thing is, here we are also combining the different augmentation, and sometimes it makes it really hard for the autoencoder to reconstruct. But if you train longer with more data, it will be actually quite robust to many augmentation. So I will just give you some seconds in case you have some question or think that we're not clear for that part. And we can actually update again the autoencoder, because this file is saved by this script from time to time. Okay, here the training is done, but as we saw it was probably not enough, so we're going just to continue for 400 more epoch. And while we do that, we can inspect again. So to continue training, we pass autoencoder parameter minus AE, and this should do the trick. Yes, continuing training. I will just reorganize everything again. So we have the cropped image, the reconstructed image. And here we see that already after 200 epoch, we reconstruct the main feature, which is the line, which will allow, oh, Maxim, good evening. Which will allow to the array legend to actually orient itself. And that's something that we want. So how do you select the size of the latent space? Will, for example, 64 led to significant better result? So the way I selected is I tried to have the smallest dimension that works. That works mean that the reconstructed image makes sense. And would that lead to, if you double it, would that lead to significant better result? So far I did not see it. At least what improved result for me was to add data that was not so well reconstructed by the autoencoder and continue training. So what worked best for me was actually training more with additional data and data that was hard for the autoencoder, rather than augmenting the size of the latent space. I hope that answered your question, Rainer. Okay, so here we see that our continued in. We can also just take a look at the loss, which is already much better than previously. And the other thing that is with the Android script, we can have also a quantitative measure of what is the mean error, the max error, and the median error for reconstruction. And if we, so here, for instance, the mean error was around 74, but if we load the latest model, and for the name, we're just going to copy paste it from this terminal. Okay, so if we load from that one, because it's the autoencoder that has more training, it should also reconstruct things better. And here we start to see also not only the yellow line, but also the white line. And once we have reconstructed both the yellow line and the white line, then it should be already good enough for training a RL agent. And here we see that the error decreased. Okay, so while this continued to train, the next things we want to do is actually integrate that part into for training the RL agent. And for that, we're going to use what's called a gym wrapper. So if you want a gym wrapper, you can directly take a look at the code. In fact, for any wrapper, for instance, if let's say a wrapper is just something that will be applied to the environment and that will modify either the action and or the observation. And for instance, one simple wrapper is to clip the action, and it will do some pre-processing or post-processing step to our environment. And the idea of wrapper is that you can reuse them easily, in the sense that we could use the autoencoder and integrate it directly in the gym environment, so in this environment, but we won't be able to reuse it or to change things quickly. So let's see how do we do a wrapper. The other thing that you should know is in autoencoder we have a nice helper which is called load autoencoder, which allows us to quickly load this trained autoencoder. And the function that is very helpful for us will be, it's called encode from raw image. What it does some pre-processing. So here it just divides the values of the raw values by 255 to have something normalized between 0 and 1. And then it encodes it using the pre-trained encoder and return then the latent vector. So in wrapper there's actually some code, but we're going to actually delete it. So you see how to do that. So the thing we need to create the wrapper is to import gym, import from the package autoencoder, which is this package, the load autoencoder function. And here I added also some type hints for later on. So the first thing we need to do to define the wrapper is actually make it inherit. So we will call it autoencoder wrapper, and we will inherit from gym wrapper. So the main thing of gym wrapper is that it receives an environment, so which is a type gymenv as input. And for us, we would like also to give a path to an autoencoder. And to make things easier, I will also allow it to be an environment variable. So in case we don't overwrite it, let's say that we will call it autoencoder path. And this will be an environment variable that we can set in the terminal directly. Okay, then we call the constructor and passing the env. And the first thing we need to do then is to to load the autoencoder. So we're going to say self.autoencoder is load autoencoder of, and we give the path to the autoencoder. The next thing we need to do also is change the observation space. So if you recall, and that's what we are going to see right now, if you go to Gym DonkeyCar in env and DonkeyCar env, and you search for observation space, the observation space currently is the image. So it's a box, and the sensor size is at the end you get an image with 3 channels. And this we're going to change it because we're going to encode the first image with the encoder and then output the latent vector. So we are going still to have a continuous action space. So this is where we have a box. We're just going to set load to infinity. This is not required, but as we are not sure of what is our lower and upper bound of the autoencoder, we can just set it to -infinity and infinity. The type will be float32. And the last thing we need to give is a shape. So the shape will be actually the size of the encoded image, and here we can directly retrieve it from the autoencoder, the loaded autoencoder. Okay, and I'm just going to reformat everything using make format. So it's using black and ISOR to reformat everything nicely. That's what I'm doing. So currently what we did is we changed the observation space, and instead of having an image as input, we say that we have a vector of size z size, which is a latent vector size, as input. And so we also need to change the step and the reset function. So we're going to first change the reset function. And the reset function will return a numpy array, which is the encoded image. So for that, we first need to reset our environment using self.env.reset. And next things we need to do is encoded image. We're going to encode it using the autoencoder. So for that, we call the encode from raw image. And here there's actually a trick, because this will give you RGB image, but because we are using OpenCV to load everything, our autoencoder is using BGR images. So we just need to flip the last channel to actually have the correct order of channels. So instead of RGB, we have BGR. And once we have done that, we can just return the encoded image. And we add a comment, convert to BGR. So that's for the reset. And for the step, which take as parameter an action, which is the throttle and the steering. And we will return, an observation, so numpy array. We will return the reward, we return the termination condition, and we will return also the information dictionary. So again, here we need just to step in the environment, self.env.step, passing the action that we have, and we retrieve the observation, the reward, if it's terminated, and some information. Again, we encode with a pre-trained autoencoder, and we can just copy paste here. And what we do is we return everything except the observation, because we return just the encoded observation. Okay. And that should be fine. We can actually check using make commit checks. It will also check if some variables are not defined using pytype and flag8, and it will lint the code in case we have some variables that are not used or some imports not used. And I take advantage of that to both ask you, is there any question or thing that I should repeat or not? And here, okay, here we have spaces, which is not defined, and that's true. Here spaces is directly from gym.spaces.box, so we have a vector of that size, and that should do the trick. Let's just lint it quickly. Yeah, optional is not defined because I just use a different way of defining things. Okay, so all good for Maxim, and for the others, I think you can always chat in the chat if there's anything to add. So here it's just a wrapper to encode input image using pre-trained autoencoder. And the first parameter is the gym environment. And the second parameter is the pass to the absolute pass to the pre-trained autoencoder. Okay, so next things we're going to try right now is actually see if everything is working. And as a debugging, step, we could even here, and we're going to do that. We're going to reconstruct to plot the reconstructed image. So for that, in the autoencoder, we have a decode. We have a decode function, and we can directly pass normally the encoded image. Here, decode encoded image. And next things I'm going to do is just quickly reuse some OpenCV code I have in the test script. So in the test script, I'm using OpenCV to plot and display images, and that's what I'm going to do. So if I recall, it's called cv.window .display probably. No, image show. Okay. And we can again plot the original, which is the observation here. Don't forget to actually convert it to BGR, otherwise you will have weird things. So we import OpenCV. And we want the reconstructed image, and the reconstructed image is decoded, and we take the first of the batch. Okay, here we go. Reconstructed image. Here we go. Yeah, thanks, Maxim. Image show. And this won't work. We just need to also wait for a key, otherwise it won't display anything. Okay, so what this wrapper does currently, I will apply it around the gym environment, and instead of actually normally stepping into it, we will have we will show the image and reconstruct the image. And here again, we're going to just quickly check that no mistake were made, and in the meantime that the checker is done. Break is outside the loop. Yeah, that's true. I think we're just going to pass for now. What we can do now is start a terminal, import gym DonkeyCar, import gym. We have our package which is called Autoencoder, so it's called Autoencoder. We will start again the simulator because we want to interact with it. Okay, simulator is ready. Next things we need to do is actually retrieve the path to the autoencoder, and so the path is this absolute path plus the path to the log. Here we go. And then we can do a gym.make to create the environment and connect to the simulator, which is if you go to record data, you have the actual ID of the environment, and you can change the ID to have a different track. Now we just copy paste it, so it's Donkey Mountain Track version 0. Okay, so we connected to it, and now we're going to wrap it using our wrapper. So it's autoencoder.wrappers. It should be from dot wrapper import autoencoder wrapper. Yes. And AA path is not defined. That is true. So here we're just going to, oh yeah, we can then set the environment variable using the path we just defined before. So the path is there, and normally we can import now. Yes. Now we're going to wrap environment, and for that we're just going to call the autoencoder wrapper around the environment. Now we can reset it, and normally the observation will be then will be of shape 32. Observation, the shape is well, it's 132. We should actually fix that. So we go to wrapper, and in encoded image we need to flatten everything because we define it as a 1D vector, so just of size 32, and here we had 132 as a shape. So once we have defined here, we need to flatten here, and we need to flatten it also here. Okay. And then we can just step in the wrap environment, and normally it will show us the reconstructed image. And here we're just going to pass 0 throttle and 0 speed. And so far it looks pretty good. So it's the original image, and the reconstruction is fine. So it means that the pre-processing here is actually working well. And just as an example of what may happen, probably I could disable, if you disable here the conversion to RGB, then the reconstructed image will be much worse. So that way, by looking at the reconstructed image, we can actually be sure that everything is fine. And for instance, we can give some throttle to see if it doesn't only reconstruct the starting line, but also the rest. And that's why we see here. It's not perfect, but at least it recognizes the lines and things. Okay. Is there any question? So so far we are quite close actually to start training with a pre-trained autoencoder. And once we're done, we can again reset it. And maybe just to demonstrate, is there a way? Oh yeah. So what will happen if you don't pre-process the same way I will just use the unwrap environment. So here the observation will be actually the full image, and I will encode everything and decode everything, but not doing not converting it to BGR. And it's wrap env that we encode it, we decode it, wrapped env, and we will display the wrong reconstruction. We don't need to import OpenCV. It doesn't show anything because it's waiting for a key for that. Yes. So it's not as good as before, and we see some artifact and the color are probably not right. And this is usually a symptom that you did something wrong between training and testing, or between training and deployment. You have something wrong, and you should always check that. You should also check the reconstruction error, that it should be more or less in the same order of magnitude of when you tested your pre-trained autoencoder. All right. So far so good. No question in the chat. Because if that's the case, then we can actually we are really close to training the agent. There's just something I would like to add is I would like to also add the speed as information for the agent in the observation space. And here you can quickly modify the wrapper. So I will comment out all the reconstruction part. And I would like to include the speed also to give the actual speed of the agent to the agent. And for that, we're going to add just one dimension to our vector. And here we're going to, the new observation will be concatenate of two things, of the encoded image and of 0, 0. Which is the speed at the very beginning. And the same goes here. Here we actually retrieve the speed of the car from the info dictionary here. In the info dict, we look at the key speed. And we will concatenate it with the encoded image and return everything. All right. Let's check if actually that works, because that may be a problem. So again, we import Jim, import Jim DonkeyCar, and import our wrapper. Define the path. We should have actually defined it directly. Let's define it in the terminal. We export a autoencoder path to the path of our autoencoder, and then we can re-import everything, Jim DonkeyCar, and import our wrapper. From added wrapper, import autoencoder wrapper. We can create the environment and rewrap it. And autoencoder wrapper of the environment. Okay, and if we reset, so far so good. And yeah, that's what I thought. There's issue with encoded the image. I think we need to flatten that one here and flatten it here too. Let's just do a quick check. If our encoded image will be a vector of size 32, and we're just going to encode that. Encode it, and yes, we have a vector of size 33. This should solve the error and everything should be fine. And here we actually should pass the speed. So to sum up, what did we do with the this wrapper? With the wrapper, we encoded the observation with the autoencoder. We added additional feature, which is the current speed of the car, which is actually very helpful if you're racing. And we are passing everything to the agent. So that was for yeah. So this was for the autoencoder wrapper, and now the last part of the video will be live will be actually about plugging it with the RL training and starting training. And before I do that, if there's any question, again, please post in the chat. So for the last part, we're going to use the RL Zoo, which is a training framework for reinforcement learning agent. It has many things included. And again, we can start cloning it in the repository where we want it. Okay, maybe in that one would be better. Document RL racing live number 2, and we can clone it. And we will also open it in our editor. Okay, I will remove that one. We open it. So it has many things. It has hyperparameters for different algorithm and different environment. It has training script, Android script. It's quite helpful for also saving checkpoints and doing other things like that. And we are going to check out a specific branch which was made for the DonkeyCar, which is called the offline RL. It's a bit cleaned up, and if you look at hyperparameters in TQC, there's the environment that we actually want. We will actually change that name to the one we are interested in. If you go to Donkey Mountain Track, okay. So the way it is structured is for each algorithm, there's one file, one configuration file for hyperparameters, and for instance for A to C, and for each environment, we override some defaults to have tuned hyperparameter for each of those. And the zoo will keep track of the hyperparameters that you used, and also the other thing that you passed or not to the environment. So here it's pretty. So let me just clean that up. Okay. We added so a time limit. So in this file you can define different wrappers and different callback. You don't tackle. I won't get in the detail of the training hyperparameters here. I will mostly get into the details of the callback and the wrapper. So here I added already one wrapper, which had a time limit, so it has a timeout, so that if one episode is too long, it will reset it. it's usually helpful if one agent is stuck and your termination condition does not detect it. But we would like also to add something else, which is our wrapper. And here, so we can directly call it. So it's called from the package Autoencoder, from the file wrapper. Here we go, and it's called Autoencoder wrapper. And we could, I will not do it because we already have environment variables for that. We could actually also set hardcode the path to our autoencoder, which is, if you recall, it's this string plus the one from the terminal. Here we go. So we could hardcode it, but we are going to actually use environment variables, so we don't need that. So what it's going to do is we're going to wrap it with a termination condition with the autoencoder, which also gives you the speed. And we will normalize the input because the autoencoder output is not normalized, and it's always a good practice to have normalized observation. And once we are done with that, what's going to happen is we have a callback, which will, so there will be data collection on one thread, and on another thread there will be model training with 200 gradient step taken every 200 step of data collection, and this will be in a separate thread. So that way we don't have to wait for the gradient update to finish to collect more data. And we can directly try that out. So if you go, make sure to have the simulator launched. Yes. Here I will just probably also going to change some setting, which is a timescale, make it 4 times faster. Thanks, Maxim. It's a nice feature to have on simulator. And save. And here we go. We are in our RSU repository, and we need to call Python train the algorithm, which is called TQC for truncated quantile critics. The environment is a donkey mountain track. We are not going to create any evaluation environment, otherwise it will create 2 cars on the track. And we can say that we want to save a checkpoint every 25,000 steps. And I think we are good to go. Is there something else? We could also save the replay buffer in case we want to continue training later on. And normally, so if I launch that, normally this will fail. If I did not define, let me just do something. Let me define the autoencoder path. So I define it with export variable, and normally this should start training. So here we see there's a small bug, and that's what I actually tackled in my auto branch, which is at the very first reset. The speed is not really set to 0, and if you take a look at my branch here, when I prepared the live, there's additionally some tweak that I do at reset, which is taking again some no action, so that it really starts from 0. But this is minor detail. And here we can just keep a look at the training, and there will be normally, here I did not add all the bells and whistles for good RL training, so it will train an agent that would work and would work quite quickly, normally like in 10-20 minutes you will have something that does the full track, but it will usually wiggle around a lot. And that's probably what I will tackle in another live, or I can just quickly talk about it today, but I don't think I will have time. Which is, how do you make the driving smoother and also better? The other problem here is that we reset it every time it touches one object, and we can be also more lenient with that, and for instance reset it only it touches 2-3 times and allow it to recover from actually touching something, colliding with something. And so at the very beginning, early training, it's very stupid, and in fact there won't be any gradient step before a while, if I recall. It's a learning step. Before 5,000 steps it will just take random actions, and after 5,000 steps it will actually start taking gradient step. And so you have the episode length, which is interesting for us, and also the episode reward. Maybe let me just restart everything, but I've also logged that to TensorBoard in /tmp/sb3, and we're just not going to, we're going to start from much earlier, let's say 500 steps. So here directly with the command line you can change hyperparameters, and those hyperparameters will be saved. And here I'm logging to TensorBoard because I think this will be more visual to see the progress of the agent over time. Okay, so that's one thing. And we see here it's a TensorBoard log, and we can actually launch TensorBoard in another terminal, log dir. So TensorBoard log dir, here we go. And you can, it will launch a server, and we will have updated figures once it has trained a bit more. Okay, so this is TensorBoard, this is our training, we don't care about that anymore. Okay. And normally this should update also automatically. We should reload every 30 seconds. So at the very beginning it won't do much, but soon we hope that both in terms of length, so it will stay longer without colliding, and it will also get higher reward. So currently the reward we are using, if I recall, is the cross-track error. Okay, so now it's time for questions, in case you have any. And then I will probably let it run longer. And maybe as a summary of what we did today. So today we started with a recap of what was done last time, and what was done last time is already saved and online on GitHub. Then we took a look at the autoencoder, augmented autoencoder, denoising one, how to collect data for it using random driving. You don't need to be a good driver, and I'm not a good driver, so that's the good news. And then once we have we trained the autoencoder, we tested what was learned, and by taking a look at it, we decided to continue training. And finally, we wrote a small wrapper to actually use it with our gym environment and plug it in the zoo. So so the command line that I use, so everything is in the README, otherwise also of the RSU. But basically, I will rewrite it. I will try to take it and rewrite it. Let me show you in another terminal. Or maybe here. Soft wrap. Okay. Should be bigger. So basically, the command line, what we did is Python train. Then you pass the algorithm you want to use. Then the environment you want to use it on. Maybe I should still have the car next to it. How often do you want to evaluate your agent on a separate environment? Here we don't have two agents, we have only one robot, so we deactivate it. And then we want to save a checkpoint every 25,000 steps because the performance can vary. And we want to save the replay buffer. I also additionally ask for a TensorBoard logging using -tb. And here I just gave a pass where I want to save TensorBoard logs. And finally, I quickly changed some hyperparameters using the -params option. And what I changed was the learning starts to actually start the gradient update quickly, and I changed it to a certain value. So yeah, I will upload the video on YouTube afterward. And there's already the first video on YouTube. Best if you want to take a look at where to find me is to go on my website. So training without stable replay buffer will result in non-valid models after retraining. No, they will be still valid, but the thing is you will need to fill up the buffer again to so that the training makes sense. The problem is if you don't save the replay buffer and you continue training, it may explore regions that are bad, but that it forgot it was bad. Well, if you save the replay buffer, it will save all what was done before, and it will prevent exploring again regions that were known to be bad. So it's not invalid, it's just yeah, you may need to use again the learning start parameter to refill the buffer before continuing training. But that might be helpful actually to discard the replay buffer if your data change or if your reward changed, because you don't want to use the old reward function, you want to use a new one or the updated one. And that may be a reason to discard the replay buffer. Another reason to discard the replay buffer is that it takes quite some space, and you don't actually, and sometimes you don't want to save it because you just want the pre-trained agent. One thing I should probably show you. So here we can already normally see it's going a little further. Okay. What I can probably show you in addition to the TensorBoard. So here the progress is very, let me not smooth it at all. We have around, yeah, 32 FPS. We could be in fact better. And the progress is slow, but there's some progress at least. Let me check. Yeah, it's only 5 minutes, so, but there's some progress. That's at least the good news. And we should not ignore outliers. Okay. So this is a TensorBoard log. And we can actually take a look at what is currently learned. And we see that we go slightly further, but not much yet. One thing I wanted to show you is actually once you have trained, what's inside the RLZoo, what's inside the trained agent folder. So if you go to, again, Racing Car Live 2, in the RLZoo, in the logs, and we go to the logs of our currently trained agent, there's a monitor file. So the monitor file is basically logging all the episodes, and it gives you for each episode what is the episodic reward, at what time it was done, and the number of steps per episode. It allows you, in fact, to, for instance, do some, if you want to plot something, you can plot things afterward with the zoo. I will show it probably right after it. Okay, and another thing that you have in it is both the config file, which allows to actually reproduce the training. So it has all the argument, all the hyperparameter that you pass to the agent, including the callback and the wrapper. So that way you always, and also the normalization. And it has also the argument passed to the command line. So for instance, I passed, where did I pass it? Here I passed a save frequency of 25,000 and I saved the replay buffer. And this is also stored in the reinforcement learning. So yeah, TensorFlow is quite nice, but it's really lacking a lot of features that weight and biases, for instance, as. Oh, I didn't say, you can actually also record and send everything to weight and biases after during training. Okay. It sounds like reload data is not enough. And for that, you have an argument in the RLZoo. So there was another question. Are you a student researcher or something else? A bit of everything. So I'm a researcher at the German Aerospace Center, but I'm also doing a PhD while doing some research on reinforcement learning for real robots. But I've been working there for more than 3 years now. Okay, so progress is slow, but there's some progress. And the main reason of maybe why is it still slow is because we probably need to collect more data and train for longer the autoencoder. But I will keep it for 5 more minutes and probably continue talking if you have more questions. Otherwise, I will stop the live. And maybe as just a curiosity question, can you, for those who are in the chat, can you write from which country you are watching the live? No, Maxime is from France. We have probably people from Netherlands and some other from Germany. All right. Yeah. Progress is slow. Okay, so there's no question. Oh, Switzerland, nice. Yeah, so after the live, I will try to put everything, all the code online, and also put a pre-trained autoencoder, one which is trained with more data, but you can also train it on your own and see, yeah. For the next live, what I would like to dive in is probably adding additional tricks. So as I told you, being more lenient with the termination condition, add in some wrapper to make the driving smoother, and maybe doing some additional tweaks to the gym environment. I've tried to train the autoencoder with other cars to avoid crashing. Not yet, but I would also need to train the reinforcement learning agent with other car, and that makes the simulator a little slower, and that makes also the reward signal harder, because I would need to have agent already driving plus everything. So I would probably do that as a post-processing step. But if I do that, this would also mean that the reinforcement learning agent will be slower because it will learn to avoid crashes. And that was not my goal so far. So my goal so far was to have the fastest agent as possible. All right, so it's mainly barely doing the first turn, and as I told you, it can learn much faster if the pre-trained autoencoder is as a better representation. And that's probably something I can do also in another live, which is exploring other ways to encode information using, for instance, self-supervised learning and not autoencoder. And I've been trying that, in fact, recently, and it looks like it could give quite good results. So I will probably explore that and talk about that in another live. Maybe as another question, do you have something that you would like to be explored in another live, or something you would like to try or to see tried? Yeah. Yeah, the progress is slow, but there's some progress. All right, then I think we are done. Thank you for watching. Maybe see you next time. And in the meantime, I will try to clean things up and put also dataset online so you can pre-train your own and use a pre-trained one too. All right, and we can kill the script now.